Greetings, everybody. So, today we're going to have a very nice talk about chaos and how it appears in many different scientific disciplines. It's from an invited talk we had here at the University of Nova Gorica for some high school students who came to visit us. Okay, so basically, as the title says, I'm going to discuss about the emergence of chaos in many different scientific and natural disciplines, how we can use chaos to model different phenomena, and how we can use chaos in different application areas. Okay, because you don't have to be an expert in any of these topics, you just have to uh, stay tuned. It's going to be very introductory talk. So, what is chaos? I have discussed about this in previous videos as well. Okay, here we have many different images. I have the references here on the bottom, which kind of makes you think that this behavior or this phenomenon is chaotic. I mean, in a real life situation, we use chaos as we talk with one another to discuss something that's very complex or very difficult to understand. Okay, so for example, a mosh pit inside a metal concert or a rock concert seems to be very chaotic. People running around, jumping on top of each other. Okay, a very chaotic situation. Or this image that you see right here with a million different cables on the street. Okay, in real life, when we talk to each other, we would say, wow, what the hell is this? This is very chaotic. Okay. Or maybe a different, let's say a network connecting many different cities. Okay. Think, for example, an electrical network connecting the whole of Europe. Okay. This is a very big network connecting millions of different cities across many different countries. Okay. It's a very complex network, we would say. We would say it is chaotic. I don't know. And on the bottom, I have some other examples. For example, a Romanesco broccoli that is very intricate in design and it has some patterns that are self-repeating but very weird looking. Okay, brings chaos to mind. Some Jackson Pollock or some other painter that has very abstract paintings or some other patterns that are very intricate, very complex, but they seem to be sort of a pattern emerging, like self-similar pattern as you see in the graphs that I have right here. So it's very difficult to understand, is any of these things chaotic or not? Well, I'm gonna give you the definition from a mathematical and physical perspective, okay? And from that perspective, by chaos, we refer to deterministic systems. So there are systems that can be described with some rules, okay? And these systems showcase what we say it's an extreme sensitivity to initial conditions. What does that mean? This means that the system starting from slightly different initial settings, okay, will eventually, in the long run, give you completely different solutions. This is a great simulation here on the left. We have a double pendulum, three pendulums, and they start from almost the same initial condition. But see what happens within just a few seconds, although they start from almost the same point. Let's wait a bit, you see? Within just a few seconds, the solutions become completely different. Okay, so although all of these pendulums started from almost the same initial condition, almost the same point, well, in just a couple of seconds, the solution became completely different. Okay, so this phenomenon, this extreme sensitivity to initial conditions, is what we call chaos. Okay, and this phenomenon, just because this very slight change will give very different solutions after a couple of seconds, makes chaotic systems extremely difficult to predict. Okay, because this tiny change will create a very big change uh, down on the road. Okay, this is another cool example. We have two balls starting from almost the same point, and they are bouncing inside the circle. And you see that after just a couple of bounces, I'm sorry, uh, their bouncing and trajectories become completely different. Okay, let me wait to start again. You see, first, second, third, and after the fourth bounce, the trajectories become completely different. This is an example of a chaotic phenomenon. Okay, so this is what makes the solution and the trajectory extremely hard to predict because even a slight change will give you a completely unpredictable solution. Okay, this makes chaotic systems extremely hard to predict and analyze. Okay, this is another very nice example. the water wheel of Lorentz. Imagine having a water here, a water wheel, so water drops down, and each of these buckets has a small hole in it. So the water comes in and gets out. So it's very difficult to predict how this wheel will go about. So you can have it turning around 10 times right here and then it stops and it will turn counterclockwise once or maybe twice or maybe three and then go back and then right, left, right, left. And it is extremely difficult to predict how it will go. It will go, for example, 10 times right and then once on the left, or maybe it can go one on the right and three times on the left and then back and forth. The pattern is completely unpredictable. Okay, so this is an example of a physical chaotic system. And here I have a very nice simulation. So what you see here is basically I have a chaotic system and I have 50 different solutions. And all of these 50 different solutions start from almost the same point, near zero point 0.1. So see what happens. What you see right here is actually 50 solutions, okay, not just one. And as the solutions progress, initially they're all very much looking the same. That's why you don't see any difference right here on the first 30 iterations. So this very small difference keeps remaining small for a lot of time. So it small, you cannot see it. But in due time, eventually this small difference becomes larger and larger and larger and larger and larger until eventually these 50 different solutions become completely different from one another. Okay, so this is why it's very hard to predict. This small change in the system, initially, it was not even observable to me. I could not even see this difference. But after some time, eventually this difference became bigger and bigger and bigger until eventually all solutions become different from each other. Okay, so this is the butterfly effect. A small change at the start leads to huge changes down on the road. Okay, so this phenomenon actually is super common. Super common. Basically, I would say that non-chaos is the exception. Okay. The normal behavior in all of natural systems is chaos. Okay. So it appears everywhere in nature and in man-made systems. In engineering, it appears in vibration, in robotics, mechanical systems, okay, it's chaos. In biology, for example, in predator-prey scenarios where you have rabbits and plants, where you have rabbits and foxes, and different populations interacting, you have chaotic behavior. In human physiology, okay, our heart, for example, is a chaotic system, and other parts of our body are also chaotic. In astronomy, in moving planets, in economy, for example, is a very chaotic system. In chemistry, in circuits, we have a lot of chaos appearing in circuits. And I would say all phenomena are chaotic. Non-chaotic phenomena are actually an exception. Rarely we see non-chaotic phenomena in nature. Okay. So one very big part of chaos theory is modeling natural phenomena. Another part, chaos, is to use chaotic systems in several applications. Because we can very easily simulate in a computer chaotic systems, we can use them as a source of randomness to encrypt data, to perform watermarking. We can use them in robotics, in many different applications. And this is about what I'm going to talk to you today. Okay, so let's start giving you some examples of chaotic systems. Now, first of all, regarding mathematical modeling, okay, this is a topic that mostly mathematicians and physics worry. Now, chaos, as I told you, is a very complex phenomenon, and when we are studying chaos in a system, basically we're also studying how does chaos appear there. Because chaos is related with many different phenomena. One of them is periodicity. So basically, when a system behaves chaotically, it usually transitions into chaotic behavior little by little. So it may start with very normal behavior, as you see here on the top. Okay, these are all very normal periodic behaviors, but may eventually become chaotic. So one big part of mathematical modeling has to do with studying how we go into chaos and also how we go out of chaos. So how do these transitions appear? And another question is, of course, which is a bit more abstract, how strong is chaos? Okay, we have tools to measure how strong is the chaotic behavior in the system. Okay, Just to give you an example, if you see the image on the right here, here we have the behavior of a specific system for different values of its parameters. And what you see right here, color is chaos and black is non-chaos. So basically, if you see it as a very nice example, as I'm changing the parameters of the system, you see that we have changes in the color. So basically, the system goes in and out of chaos as we change its parameters. And you see that here we have very, very weird patterns, okay? And actually they are a bit self-similar. So we have chaos order, chaos order, chaos order, chaos order, as we are changing the parameters of the system. And this transition in and out of chaos, as you see, is very, very complex. That's why we have these weird patterns right here that indicate that we go in and out of chaos in a very weird way. Okay, so this is a very common phenomenon, and from the mathematical and physical perspective, we are trying to understand why it happens. This is a topic for pure mathematicians. Now, another topic, as I told you, is modeling chaotic systems. Okay, and one case where chaotic systems arise is in neural networks and physiology. So basically, in physiology, let's say about human physiology, a lot of parts of our body behave chaotically. What is interesting here is that the fact that we have chaotic behavior can be either good or bad. So when a system behaves chaotically, it's not a bad thing. It's not necessarily a good thing either. It has to do with the application. So for example, in a very common neurological disorder, which is attention deficit disorder or hyperactivity disorder, where we cannot stay focused for a lot of time in a specific task, okay, there in a neuronal, response, chaos can be a sign that we're losing focus. So here in ADD, the rise of chaos can be a bad thing. Chaos means that we cannot stay focused on a specific topic for a lot of time. So here chaos is bad. But in other applications, let's say for example in epilepsy, okay, when in a neuronal response you have an onset of epilepsy about to appear, then the system exits chaos, okay, it becomes non-chaotic. So here, non-chaos is a sign of a bad behavior. It's possibly epilepsy. Okay, chaos is a good thing in a neuronal response in the brain regarding to epilepsy. Okay, when we exit chaos and we become periodic, then we have an onset of epilepsy. So in this case, chaos is not a bad thing. And this is very interesting because, as I told you, you can have chaos meaning a good thing, or you can have chaos meaning a bad thing. So this is very, very, very nice. Okay. This is basically what you will see in chaotic neural networks. We have very simple neuronal models, and we're trying to see as the information propagates inside the network. So let's say we have a circular transition of information, it goes back in and out and in and out again in a circular fashion. We're trying to see how the information changes. And we may see behaviors like that, where the system is almost periodic and then it has some small jump right here, and then some small jump right here, and then some small jump right here. This is very, very common. By the way, this is called intermittency. Okay. We can observe, of course, other behaviors in such type of neural networks. Again, in such networks, it is very, very common that we transition in and out of chaos, in and out of chaos as we change the parameters. So a very common phenomenon is that we are very, very, very sensitive to changes in the parameters, and we can go in and out of chaos constantly. Very complex phenomenon, very difficult to interpret as well. It's very difficult to understand why this happens. Okay. So this is one example in physiology. Another example that I mentioned is mechanical systems. So here, for example, in various systems that model vibrations, okay, we can have the system behaving chaotically. One example is, for example, vibrations in trees. Okay, we have a tree trunk and the tree under the influence of wind can vibrate chaotically. Not necessarily a good or a bad thing, it depends on the application. Another case where a system can behave chaotically is this mechanical system, which is called vibration energy harvester. These are basically systems that vibrate and through vibration they collect energy. And such systems can indeed behave chaotically as well. Okay, so it's very common to have vibrations in physical systems that showcase chaotic behavior. Okay, which means that the vibrations are continuously unpredictable. Okay, this can happen in vibrations as well. Now, of course, the modeling of chaos is infinite. We have numerous applications for modeling chaotic systems. Okay. And apart from applications, I told you we can, apart from modeling, I'm sorry, we can also use chaos as sources of randomness for various applications. So one such example, for example, is random bit generators. The idea here is this. We have our computer, we choose a chaotic system, we simulate the chaotic system, and then what we do? We can use some sort of a function. Okay, it's called a hash, but it is basically a function to be very simple. And through this function, we can take the solution of the chaotic system to generate random numbers. Okay. And the idea is that random numbers are used in various applications relating to security. So by using chaotic systems, we can easily and fastly generate random numbers. Okay. There are some challenges here. For example, we need to have very fast random number generation. We need to have very, very random numbers. Okay. And by that, I mean that statistically, we need to have very, very strong randomness. And of course, another topic that has to do with security is that we need to have, I'm sorry, generators that can be very, very hard to crack. Meaning that if someone wants to steal our method, they cannot steal it. So it's very, very secure. So they cannot find information about the chaotic system. So random number generators are very, very common using chaos because they are used in applications relating to security. One such application, for example, is a password generator. Here we can give it some initial information about us and we can ask it to generate a random password for us, okay? And just because we are using chaotic systems, in this case, the random password is not only secure, but also we can replicate the password if you like. Okay, so we can basically have a very secure password, a very random password, which we can generate again and again and again in case we forget it. So it's also secure for us. Another application of chaos, which I also do a lot of research in, is chaos encryption. The idea here is in chaos encryption that we are using a chaotic system in order to encrypt some information. Let's say I want to transmit some image. I'm using the chaos system to hide information in this image and how can I say this? Scramble the information in the image, safely transmit it, because basically now the image is like noise, you cannot understand it. And then once my receiver, my friend, takes this information, they can reverse the process to obtain the original image back. Okay. And the classic way for encrypting data has to do with two specific processes, and we're doing them using chaotic systems. Okay. So one type of encryption is shuffling. Imagine taking this image and shuffling the pixels in the image. Okay. And I can do that using chaos. And another action is called substitution, where we basically, how can I say, substitute the information in the image. And again, we do it using chaotic systems. So imagine having a chaotic system that tells me how I will encrypt my data. Okay. And this is very useful because I can also reverse the process to obtain the original information system back, the original information image. Okay, so we can go from this point to the middle point to the right point using chaotic systems. Okay, a very, very nice application. And of course, we can also use this application in an app, as you see right here, where we can load our image, encrypt it, use some secret information in order to decrypt it and obtain the original image back. Okay, so this is a very, very nice way we can implement our algorithms in some applications that are easy, very, very easy to use. Okay, and then I'm gonna give you one more application, which is chaotic path planning. Now, in path planning or in patrolling, our goal is basically to go around a specific area and cover the whole area. In chaotic path planning, on the other hand, our goal is to do some unpredictable moving. So the idea is that we have some sort of robot moving around the area, or a UAV maybe, and instead of moving in a specific pattern, as you see right here, we are moving in an unpredictable pattern. Okay, and the idea is that this unpredictable pattern is secure against, for example, intruders who want to go inside our secure area, and possibly for other applications like household cleaning, like firefighting. But in general, in chaotic maneuvering, we can get an additional sense of security because we are moving unpredictably in the space. So we can use chaotic systems to do that. Okay, the simulation may look something like that. Okay, when the agent moves around unpredictably, and I have a bigger simulation right here. So basically here we have a chaotic system that gives us navigation commands to move around the area. And of course, a very big part of this application is optimization, meaning how we can move better and better and better in the space. Okay, because here, for example, this is not very optimal, but I can actually design algorithms to optimize it. Okay, so this is a case, for example, where we are a bit more optimal and we can have a much better coverage in time. Let me run it again. You see that we are very, very quickly covering the whole area. Okay, I have, I think, more simulations. You can see right here. This is another form of optimization where we basically break down the area into sub areas and cover each sub area. So a very, very big topic here in chaotic path planning is trying to make the coverage as good as possible, as efficient as possible, but still managing to maintain unpredictability. Okay, I have more simulations, I think. Let me see. Yes, I have one more when the system is a bit more smoothly, but still moves unpredictably throughout the whole area. Okay. And the final application that I'm going to give you is chaotic circuits. Now, I don't do research on circuits, by the way, but if you search a little bit in the literature, you will see that by using chaotic circuits, basically circuits that oscillate in a chaotic way, what we could do is basically design a secure protocol, sort of a chaotic signature that is unique to a specific circuit, which means that an intruder cannot hack us because this unique signature is very, very hard to replicate. This is called physical unclonable functions. And as you see from the title right here, it's a hacker's nightmare, programmable chips secured by chaos. And the idea is that we have some part of the system giving us a unique signature through chaos, which cannot be replicated. Okay, I'm giving it to you in a bit unscientific way because it's a bit more complex design. So again, a lot of people do chaos in circuits, okay, in order to secure them, or in general, as you see right here, in order to replicate chaotic systems. Okay, so what you see right here are basically devices that manage to replicate different chaotic systems in a microcontroller, okay, in an actual circuit, which is very, very interesting. I don't do research on that, but it is a very, very interesting topic. So as you can see, we can have basically many, many different applications of chaos in security, in communications, okay, in path planning, many, many different topics. But actually, you can go even further than that and apply chaos in much more abstract ways. So, for example, even in artistic disciplines, you can use chaos, for example, in combination with programming, if you like machine learning or even simpler programming, in order, for example, to design music. Okay, I have some example here. I'm not sure if you will be able to hear it. This is an example of music that is generated using unpredictability and a very, very simple algorithm to generate this sort of unpredictable pattern for dark ambient music. Okay. So it's very easy to use chaos as an inspiration to even do artistic stuff, like the one that you hear at the moment. Okay, this is a specific program that I'm working on right now. But if you see other works as well, here, for example, some very, 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 very cool people designed what is called Lebaton. Lebaton. It's a musical instrument that uses a triple pendulum. Okay, I advise you to go into YouTube and see that. They have an amazing application where the triple pendulum goes around and generates music chaotically, and it gives you a very nice futuristic sort of music. I really like that. It's very, very cool. I strongly suggest that you Google that and watch this video. It's amazing video. Very, very cool. Okay. So we saw like what, 10 different applications of chaos, 15. I mean, there are a million applications of chaos, which begs the question, what should my scientific background be in order to study them? Okay. So it's not something to panic. Okay, you don't need to learn everything in order to be able to study chaos. Okay, you need to have some basic information in dynamical systems. Okay, certainly some knowledge about programming. So you should know how to program in Python, MATLAB, or whatever you like. And then some information about the specific application. I mean, if you're working on biological systems, you need to know some basic biology. If you're working on economical systems, some basic economy. Okay. If you're working on encryption, you need to know some basics of encryption. If you're working on circuits, you need to know some basics of circuits. But this sounds like a lot. You don't need to panic because basically we don't learn all of that in a month or in a week or in a year. Okay, this is information that if you go to the university, you will learn across many, many years, 3, 4, 5 years, even more. So we learn all of this stuff little by little. Don't panic if you're a high school student or a university student and you don't know about this stuff. Don't worry, I didn't know about them. I studied them and learned them little by little over many, many years. So there is no need to worry here, okay? We need to start learning, but we have a very long learning curve ahead of us, okay? And you definitely, definitely don't need to be a genius. Don't worry. If chaos sounds difficult, you don't need to be a genius to study chaotic systems, okay? You just need to be intrigued by them and just have to study a little bit. But if you study, you don't need to be an expert, you don't need to be a genius, and you will still manage to do amazing stuff on chaos in any application that you like. So don't worry, start studying. It's an amazing discipline. Okay. I need to say, of course, in my channel, I have a lot of playlists regarding chaos and encryption, so you can learn a lot of stuff by watching the videos from my channel. That's the things I had to say to you. Thank you very much for watching this lecture. If you have any questions, just write them down in the comments. Okay. And I guess I'll see you around, but please be tuned. Ask me anything you like. I'll try to help you. Okay. Thank you very much.